A tiny, frozen world nearly 4 billion miles away is currently doing something that should be physically impossible for our instruments to see. Floating in the absolute freeze of the Kuiper Belt, Pluto is so small, so dark, and so impossibly distant that it appears from Earth as nothing more than a featureless point of light, lost in a sea of background stars. Yet, the James Webb Space Telescope has just bypassed the physical limits of modern optics to capture something astronomers thought they would never witness in their lifetimes. It has decoded the chemical and thermal reality of this dwarf planet with such precision that it has upended our entire understanding of how atmospheres behave at the edge of the solar system. If you want to understand the true scale of what we have just accomplished, you have to realize that this observation should have failed. To understand why this moment is causing such a quiet panic in the planetary science community, we have to look at the brutal physics of distance and light. When the James Webb Space Telescope was designed, its primary mission was cosmological, to peer into the deep, dark, empty voids of the early universe and capture the highly redshifted, faint infrared glow of the very first galaxies. Its mirrors are coated in a microscopic layer of pure gold, optimized to collect light that has been traveling through the expanding fabric of space for 13 billion years. It was built to look at things that are unimaginably massive and incredibly old, sitting almost completely stationary relative to our perspective. It was absolutely not built to track a tiny, cold rock hurtling through our own cosmic backyard at tens of thousands of miles per hour, reflecting almost no light of its own. The physical scale of this challenge is hard to overstate. From Webb's vantage point at the second Lagrange point, 1,000,000 miles from Earth, Pluto spans an angular size of just 0.1 arcseconds. To put that in perspective, trying to resolve any detail on Pluto's surface from that distance is mathematically equivalent to trying to read the writing on a dime held up by someone standing 40 miles away. Under the classical laws of diffraction, a telescope's ability to resolve fine details is strictly limited by the size of its primary mirror and the wavelength of the light it is collecting. Because Webb operates in the longer wavelengths of the infrared spectrum, its theoretical resolving limit for a target as small as Pluto should have yielded nothing more than a slightly warm, blurry pixel. Yet, what Webb actually delivered was not a blurry pixel but a masterclass in modern spectrographic analysis. It did not just see Pluto, it dissected it. By utilizing its near-infrared spectrograph and the mid-infrared instrument, Webb split the microscopic stream of photons returning from Pluto into their constituent wavelengths, exposing the precise molecular vibrational frequencies of its surface and its atmosphere. For decades, astronomers believed that obtaining this level of chemical resolution would require another dedicated, multi-billion-dollar flyby mission, a spacecraft that would take at least a decade to build and another 10 years to travel through the freezing void. Webb bypassed that entire timeline in a single, incredibly precise pointing sequence. The first major hurdle the engineering team had to overcome to make this observation possible was Webb's tracking system. Most astronomical targets are so distant that they appear stationary over the course of an exposure. Pluto, however, is in a continuous, dynamic orbit around the Sun, which means it drifts across the sky relative to the background stars. To capture a clean spectrum without blurring the data, Webb had to perform what is known as non-sidereal tracking. The telescope's fine guidance sensors had to lock onto a guide star, while the entire observator, a structure the size of a tennis court, slowly pivoted at a highly precise, variable rate to match Pluto's exact orbital trajectory. If the tracking drifted by even a fraction of a millisecond, the faint chemical signature of the dwarf planet would have been instantly smeared out and lost. But the tracking was only half the problem. The true nightmare for astronomers trying to study Pluto has always been its largest companion, Charon. The two worlds sit so close together that they are locked in a tight gravitational embrace, orbiting a shared center of mass outside the physical boundary of either body. From Webb's perspective, the angular separation between Pluto and Charon is so incredibly small that their light signatures constantly overlap. In previous attempts with ground-based telescopes, the intense thermal signal of Charon's water-ice surface would bleed into Pluto's nitrogen and methane signals, corrupting the data. Webb's massive 6.5-meter primary mirror, combined with its advanced point spread function modeling, allowed scientists to cleanly separate the two signals for the first time, isolating Pluto's pure spectroscopic fingerprint. When the raw data finally came back to Earth and was processed by researchers, it revealed a planetary environment in the midst of a dramatic, terrifying transformation. Pluto is currently moving away from the Sun in its highly eccentric 248-year orbit. Since its closest approach in 1989, the amount of sunlight reaching its surface has been steadily declining, plunging the world into a deep, century-long winter. For years, theoretical models predicted that as Pluto moved farther into the cold, its incredibly thin atmosphere would undergo a process of total atmospheric collapse. The nitrogen gas that forms its sky would cool to the point of condensation, freezing completely and falling to the surface as a global frost, leaving behind a completely airless vacuum. Astronomers assumed they would be blind to this collapse, unable to track the rapid changes of such a distant atmosphere without a spacecraft on the scene. But Webb's observations have captured this planetary scale event unfolding in real time. By analyzing the absorption lines of gaseous nitrogen and methane in Pluto's atmosphere, Webb has shown that the atmospheric pressure is indeed dropping, but not in the uniform, predictable way that scientists had modeled. Instead, the atmosphere is exhibiting wild, localized variations, with some regions maintaining a surprisingly thick layer of warm gas, while others have already frozen completely solid. It is a chaotic, dynamic climate transition happening on a world we once categorized as a dead, static ice ball. This atmospheric survival is closely tied to a chemical mystery that Webb has finally managed to map: the distribution of different types of ice across Pluto's surface. Pluto is not a uniform sphere of water ice. It is a patchwork of highly volatile nitrogen, carbon monoxide, and methane glaciers. These ices do not remain frozen in place. They exist in a state of continuous sublimation and deposition, turning directly from solid to gas and back again, as the feeble sunlight shifts across the landscape. Webb's high-resolution spectral maps have revealed that the massive, heart-shaped nitrogen plain known as Sputnik Planitia acts as a giant reservoir, pumping nitrogen gas into the atmosphere during the local day, which then travels to the darker, colder hemispheres where it freezes out in giant, sweeping wind patterns. This atmospheric transport loop is creating some of the most bizarre chemical landscapes in the solar system, landscapes that Webb has managed to analyze down to the isotopic level. By studying the light reflected off these surface ices, Webb's instruments detected a highly specific isotopic ratio of deuterium to hydrogen in the surface methane. This is not just a dry chemical statistic. It is a pristine record of the early solar system. Deuterium is a heavy isotope of hydrogen, and its abundance relative to normal hydrogen acts as a cosmic thermometer, telling scientists exactly where and at what temperature the organic molecules on Pluto originally formed billions of years ago. The ratios detected by Webb suggest that Pluto's organic material did not form in the warm, inner regions of the early solar nebula, but was cooked up in the ultra-cold, chemistry-rich environment of the outer disk, preserved in a deep freeze for over 4 billion years. The discovery of these heavy organic compounds has profound implications for our understanding of how the building blocks of life are distributed throughout the cosmos. As ultraviolet light from the distant sun strikes the methane and nitrogen molecules in Pluto's upper atmosphere, it breaks them apart. These fragments then recombine to form a complex organic soot known as tholins. These particles slowly rain down onto the surface, staining the frozen landscape in shades of deep reddish-brown. Webb's mid-infrared observations have shown that these tholins are not just passive coloring agents. They are actively absorbing what little solar radiation reaches Pluto, warming the surface layer just enough to drive the sublimation of the underlying nitrogen ice. It is a feedback loop where chemistry is directly shaping the geology and climate of the entire world. But perhaps the most unsettling revelation from Webb's observation of Pluto comes from its detection of carbon dioxide and hydrogen peroxide. While New Horizons detected traces of these compounds during its brief flyby, Webb has mapped their global distribution and found them in places they simply shouldn't be. Hydrogen peroxide is a highly reactive molecule that is easily broken down by radiation. Its presence on Pluto's surface suggests that some ongoing energetic process is actively creating it in real time. Scientists believe that high-energy cosmic rays and galactic radiation are constantly bombarding Pluto's water ice, splitting the molecules apart and forcing them to recombine into hydrogen peroxide. This means that even in the deepest, coldest reaches of the solar system, where the sun is nothing more than a bright star, a slow, radiation-driven chemistry is constantly churning the surface materials. While Pluto itself has kept scientists awake at night, Webb's simultaneous observation of its giant moon, Charon, has revealed an equally baffling story. Charon has always been thought of as a simpler, more geologically dead version of Pluto, covered mostly in inert water ice and lacking any atmosphere of its own. But when Webb's instruments separated Charon's spectral signal from Pluto's, they detected a clear, unmistakable signature of carbon dioxide ice spread across its northern latitudes. This discovery is a massive puzzle, because carbon dioxide is highly volatile and should have sublimated away into space billions of years ago under the influence of even the faintest sunlight. The fact that carbon dioxide is still present on Charon's surface today means it must be coming from somewhere. The leading theory among planetary scientists is that this carbon dioxide is not primordial, but is actively leaking out from Charon's interior. This suggests that beneath its heavily cratered frozen water ice crust, Charon may have once possessed a subsurface liquid ocean of its own, rich in dissolved carbon dioxide. Over billions of years, as this internal ocean froze from the outside in, the pressure would have built up, forcing carbon dioxide gas up through deep fractures in the crust where it eventually escaped to the surface and froze solid. Webb has essentially given us a window into the hidden internal evolution of a moon we had long since written off as geologically inert. To fully appreciate the genius of what Webb has accomplished here, we have to look at the sheer scale of the engineering that allows a telescope designed for the deep universe to perform planetary science. Webb's primary mirror is made of 18 hexagonal segments of beryllium, a metal that is incredibly light, strong, and stable at temperatures close to absolute zero. Each of these segments is controlled by tiny actuators that can adjust their position by a fraction of a wavelength of light. This level of precision is what allows Webb to achieve its near-perfect optical performance, concentrating the light from a target like Pluto into an incredibly sharp point rather than letting it scatter. Without this precise alignment, the faint spectroscopic signatures of Pluto's atmosphere would have been completely lost in the noise of the telescope's own optical imperfections. But the real magic happens inside the instruments themselves. The near-infrared spectrograph uses a revolutionary technology called a micro-shutter array. This is a grid of 250,000 tiny, individually controllable windows, each no wider than a human hair. By opening and closing these tiny shutters, scientists can mask out the light from bright nearby stars while letting only the light from a tiny, faint target like Pluto pass through to the spectrograph. This technology allowed Webb to capture the spectrum of Pluto with unprecedented contrast, ensuring that not a single photon of interest was contaminated by the surrounding field of background stars. What this means for the future of outer solar system exploration is nothing short of revolutionary. For decades, planetary science has been held hostage by the physics of rocket propulsion. Because the outer solar system is so incredibly distant, sending a spacecraft to a world like Pluto requires immense resources, decades of planning, and a massive dose of luck. And once the spacecraft finally arrives, it usually only has a few hours to gather data as it hurtles past the target at extreme speeds before disappearing into the deep darkness of interstellar space. Webb has broken this paradigm. It has shown that we can conduct high-resolution, long-term monitoring of these distant worlds from the comfort of our own cosmic neighborhood, tracking their seasonal changes over years and decades rather than relying on a single fleeting snapshot. This capability is already changing the way we view the Kuiper Belt as a whole. Pluto is not an isolated anomaly, it is merely the largest and closest member of a vast, unexplored frontier of icy bodies that ring the outer edge of our solar system. Beyond Pluto lie hundreds of thousands of dwarf planets and icy objects, from Eris and Haumea to Makemake and Gong. Until now, these worlds were nothing more than names on a map, completely beyond the reach of our finest telescopes. But Webb is currently turning its golden eye toward these distant residents, one by one, and what it is finding is a diverse, chemically active wilderness of ice and organics that challenges every theory of planetary formation we have. If you are fascinated by these real, unvarnished discoveries of the deep cosmos, take a moment to hit the like button and subscribe to the channel. We are committed to breaking down actual, peer-reviewed space science without the sensationalism or exaggeration, and your support is what allows us to keep producing this kind of deeply researched content. Consider for a moment what Webb's discoveries mean for our search for life beyond Earth. For a long time, astrobiologists focused almost exclusively on the habitable zone, the narrow region around a star where temperatures are just right for liquid water to exist on a planet's surface. But the discovery of active organic chemistry, volatile transport, and the strong possibility of subsurface oceans on worlds like Pluto and Charon suggests that habitability may not be a function of distance from a star at all. If a world 4 billion miles away, sitting in a permanent deep freeze, can maintain an active internal environment and a continuous cycle of organic chemistry, then the conditions necessary for prebiotic chemistry and perhaps even life itself may be far more common throughout the universe than we ever dared to imagine. This realization forces us to confront a profound shift in our perspective of the solar system. We used to view the outer planets and the Kuiper Belt as a cold, dead graveyard, a place where the dynamic processes of geology and chemistry had ground to a halt billions of years ago. But Webb is showing us that this region is actually a vast, slow-motion laboratory of primordial chemistry. It is a place where the raw materials that built our own planet, including the water and organic molecules that made life possible, are still preserved in their original pristine state, undergoing a slow, quiet evolution that has been running continuously since the dawn of time. As we look forward to the next decade of astronomical discoveries, the data Webb continues to collect on Pluto will serve as a vital benchmark for everything that comes after. Each time the telescope points toward this distant dwarf planet, it adds another piece to a puzzle that spans the entire history of our solar system. We are no longer just looking at a blurry dot of light in a telescope, nor are we relying on the memory of a flyby that happened years ago. We are actively watching a world live, breathe, and transform in the cold darkness of the outer solar system, proving that with enough human ingenuity, even the most impossible observations can become reality. Think about what it says about our species that we can build a machine, launch it into the cold void of space, and use it to decode the wind patterns and chemical snowfall of a world we didn't even know existed a century ago. It is a testament to our relentless curiosity, our refusal to let distance and darkness limit our understanding of the universe. What do you think is the most surprising thing about Pluto's self-cooling atmosphere? And does it change how you view the potential for active, hidden worlds in the deep outer solar system? Share your thoughts.